go back to our main code and see how we can factorize this whole problem, right? So I think this is going to be quite a long lecture, and there are a lot of, this will be quite a significant refactoring. So it will take a while, so you should grab a coffee or something that will, help you get closer to finishing this in one shot. The thing we want to do is we want to be able to do this computation without having to do this x-axis inside a for loop, which means that we want to prepare in the beginning of the day these variables inside an array to begin with, inside a NumPy array to begin with. So anything inside these for loops, as well as things like PNL stats, and we're doing this inside a for loop. We're going to try to avoid this kind of for loops because, as you said, it's inside a double for loop. It does these access statements. We can do these operations together by employing factorization. So we're going to implement our very own iterator. So this is kind of like iterates through each of the portfolio's indices, and then this I points to where we can go inside the data frame in order to obtain in order to where we want to, so like that will give us the pointer to the date and where we want to fill out the data. But we're going to implement a completely different function altogether. So let's try to have this over here. Let's first talk about what variables we need to have prepared first. So this is quite a big refactoring, so it will be a bit daunting, but okay, let's go and implement another function and say, let's call this class efficient alpha. Again, we're not trying to change the logic. All we want to do is we're going to take in similar settings. We're going to do similar things from the get-go. So this will be the same, and we want to implement these things together. So these are not using any for loop, so I'm just going to reuse these functionalities. But inside this for loop, inside the main for loop, we want to do something like for data, right? For data in portfolio data. Okay, we're just writing in pseudocode for now, right? So we're going to have information about the stock returned. So we're going to return row, go data, return row. We want to have information about close row. Because remember, we need information. Okay, let me just finish this first. Close row. And things like eligibles row, right? So row. Things like volatility row equals to this. So what exactly are we doing here? What we're doing is we're basically going to all the statements that has all this .add statements where we're accessing the data frame inside a for loop, right? For example, we're accessing these this historical data frame, right? We're accessing the volatility, and we're accessing the close value, the closing prices, right? And then you can, anywhere where you do this function access, we want to basically prepare the data so that we can use this variables instead of having to do it inside a for loop. So this is like an entire NumPy array, and we're going to use it for the factorization. And if you look at the PNL statement computation, then we also do this particular statement. So we basically prepare the returns, the close, the eligibility row, and the volatility row. So these are the things that we are doing inside this for loop, and we want to do this pre-computation and have this available to us when we reach this places inside the code. Now, in order to do that, we need to introduce what is known as a yielding function, as a generator function. So I'm not sure if you know what a generator does, but it will be very important at this point to see. Let's search a Python Fibonacci generator. Well, actually, let's just search for a general Python generator, and I'm sure real Python has something interesting to say about that. So generators will give you the ability to generate data without having to, without determining how much, what is the length, without having the whole thing inside the RAM. So, you know, it can even generate infinite sequences. For example, you can imagine what will happen is inside this function, you'll go inside, then you'll return a number, and then the next time you call the function, you would resume from this and then return the next number. So, well, you should just read the code. It's a little bit difficult to, I mean, I'm not very good at explaining, but you should read the code. So we're going to create a generator, data generator, right, and there's itself, and let's give this a skip for a moment. So we're going to instantiate these variables, right? So we want to create, say, for portfolio index, portfolio row, return I, return row, close I, close row, eligibles I, var I, var row. So okay, this might seem a bit complex, but we will explain the code. And zip. So okay, let's explain what this code is doing, right? So this can be quite confusing. Now, when we have a pandas data frame, so let's go through the pandas data frame. Okay, let's show this portfolio data frame here. So input portfolio data frame, and then let's show for index row in portfolio df.each rows. Let's print index row, and next. So let's go through what the code is doing. So let's make the function call. So when we go to that line, you'll see this. You'll see this is the portfolio data frame. When we do iter-row, so basically making a generator that yields this index and the row at the same time. So if you go up down one row, you will get 0, which is the index. Then you will get this pandas series, right? This is a newly created pandas series, and then you will get all of these values because we are yet to fill up these subsequent values. Okay, so that is how the iter-row function works. Then let me show you. Okay, let's delete this because we just used it for demonstration purposes. But now let's show you how zip works. So inside time, let's probably go through statements like even number is 2, 4, 6, 8, and odd is 1, 3, 5, 7. So when we do for even number I and odd number I in zip, basically zip takes two iterables and then sort of walks the index together. So you'll get something like now let's run this function. What you will get is it'll walk this index together. So you get 2, 1, 4, 3, 6, 5, 8, and 7. So this is the purpose of zip. So now you can imagine, right? If you combine the iter-rows together with multiple data frames, you will walk these data frames together. So these data frames should have the same number of rows, and this creates an iterable. So we will walk these data frames one index at a time, hand in hand, which means that we need to implement. Right now, we do not have these implemented, but we're going to implement them inside this post and pre computations, as well as inside this complete meta information. Right. So you can see here we have inside this for loop, we set the eligibility to the original data frame that we received, but we don't have to do that, right? What we want to do is to put that inside a separate data frame. So let's see how that is done. Okay, we want to create something like eligibles, equal to that. And then here we will just do eligibles.append, eligible, and then what we'll do, okay, no, this is what, and then we have self.eligibles.df equals to p.concat. I'm going to make a data frame out of this, so we'll use the eligibles, which is a list of appended series. We'll put that in columns, and then let's see what this data frame is about. So let's put it here, and Python 3 10.py. Now this is going to run the original function, so we'll go here. So instead of assigning the eligibility to the data frame inside the dictionaries that we pass into the alpha function, we want to sort of do it and put it inside a separate data frame. And you can see we will arrive at this. Of course, for readability, we want to set the columns to self.int. And it will be in the same order as we pass it in, because we're iterating a loop, and this concat operation creates the columns according to the order of the original array. So now this variable exists, and we can try to compute for these different variables. So how do we do that? It really is very similar. There's nothing too interesting about this. There's nothing too interesting about this. What we will do is very simple. We will have closes, do this, and then we'll do closes to pen. Take this close value, and then we will do the same thing. We would place it close here, we put it closes, we put the columns, and let's see what this does for us. Okay, we have this. So let's try to run that again. See what we got. And we get the closing prices for each of the individual stocks, which is again precisely what we were looking for. We also need to obtain this volatility data frame. So it's really the same, really. There's nothing interesting. So false, equal to this. We take false to pen. I think we don't even need these, do we? Let's take this. We can right away assign it to this here. And then we do something similar here. This VF. And let's see whether we get the correct values. So let's try to do it here. Okay, here we want to append fall, which is of all the F, and let's try to run it again. Okay, so it doesn't take in a data type of NumPy array, so we just let the conversion happen to append a series, and we'll take it from here. So They should be fine. Right, now we have implemented the return df, and then we've implemented close, eligibles, and volatility. And then inside here, we can of course do the same for returns. And well, I mean, this is really not very hard. So the addition gave us the eligibility data frame, the volatility data frame, the closing price data frame, and this software portfolio data frame should come from this over here. So this should come from basically inside this run simulation, and then we can do self.portfolio df equals to self.init portfolio settings, and we can copy and paste this. Yeah, we can copy and paste this, and we put self.portfolio df here. So now I think we can do something like for data in self.zip data generator, right? So this data should contain a zipped version of our all these data frames packaged together. So I think we can do something like yield. Sure, we can do something like portfolio I, and we get that. We have portfolio row, and I think all of these indices repeat. So does it? The portfolio is indexed by number, and the rest of it is indexed by a date time. So this, and this, I believe, all share the date time indices. So we can just do return I, create row. Let me just do that multiple times. So return I, return row, and we don't need this close I because it's same as return I. So all we need is this, and let's okay, so that's interesting. I mean, nothing's interesting yet, but we managed to arrange everything we need into a nice dictionary that we obtain. We're obtaining this dictionary in every iteration of the loop, and then of course we can sort of obtain this. So we can basically just do something like this. Data equals to portfolio I. We have access to these rows separately. So let's do that. So, okay, this is a little bit dry, but bear with me. This would help us make a code to another level. So, okay, so that's good. Now, imagine let's copy the same information. So compute this inside here. So actually, I was changing the wrong function just now. What we want to do is to implement it under a new function, which is the efficient form of the inefficient alpha class, but that's okay. Let's see. Let's go to our, let's comment this things out first, and then let's inside the alpha1 class, let's try to do from utils import efficient alpha as alpha. So this will basically use this alpha class instead and see whether we can get see whether this preparation of the data inside the generator works. Right. So here we will do print portfolio I portfolio row, and let's see if we can do that for. See what happens. So inside this main pi class, we're going to go inside this alpha1 class, which would use this efficient alpha class, which then we call run simulation on. Then we do the usual initialization of the portfolio settings and computation of the metadata, which is all over here. We just implement it. And then when we go inside the for loop, we would go into the data generator and get this dictionary. And we get this nice variables ready for us, right? So nothing too interesting yet, but as we go along, I think we have this mask, we have this nice volatility computations. So we have these nice volatility computations. We have the eligibility mask. We have the closing prices for the different stocks. We have I mean, this one we will fill up along the way, but other than that, we have pretty much all the information you need to do the P&L computation, so on and so forth, without having to go into the this dictionary and do the excesses. So I think the biggest takeaway from this lecture is that on how to use this generator function and how this iterals works together with zip to prepare this set of data, and then inside this next lecture we will see how to implement the code logic over here using the eligibility mask as well as the NumPy factorization. So this was a fairly long lecture. I think it's quite manageable. So we just go ahead and continue with the introducing more problems to work on.